of WKB. So yeah, we're wrapping up the approximation methods. Again, the idea is that with these tools, if I give you any kind of model for some kind of system, I'm just giving you a Hamiltonian or something, then you'll have all these tools at your disposal to solve for like the energy spectrum, or finding the eigenstates. And so WKB is this last method of tackling complicated Hamiltonian, which is based on the idea that eventually quantum mechanics, should reduce to classical mechanics when you have large momenta and quantum effects become negligible. But the issue is that, of course, quantum mechanics is a completely different description of, the physical reality. So it's hard to see that connection because we're dealing with vectors in the Hilbert space. It's not immediately clear how you get back to like balls rolling down hills. But it is just that, when we talk about things like bound states and scattering states, we're still just talking about, particles moving in a potential balls rolling down hills. And, a bound state would be a ball trapped in a hill and just sort of goes back and forth. And a scattering state would be just a ball passing over a hill or something like that. And that would be a scattering state in quantum mechanics, but it's still the same physics. It's just, the main difference in quantum mechanics is that the ball can go into regions where it would normally not be allowed to go, right? Classically, it can go into regions where it has a negative kinetic energy, which wouldn't be allowed in classical mechanics. So if you had a potential like this and you send in a ball with some energy, E, right? Then of course the ball could never make it past this point, because in here it would have a negative kinetic energy. So what would happen is the ball would, come in, it would hit this wall and just come back out. But of course we know a quantum mechanical ball, it'll have some probability of actually getting transmitted through the barrier, because there's going to be some tunneling across the barrier. Same thing with bound states in a sense. A bound state would be a ball rolling around in some kind of potential well. And if it had this energy, it would just kind of rattle around in here and go from this point to this point where the energy is equal to the potential. And that's what it would do classically. But quantum mechanically, we know that it actually can kind of go into this region too, where the potential is bigger than the total energy. So it can kind of move out a little bit. And we know that because when we solve for like the wave function, we sort of know what it looks like. It's very wiggly in here. That's the free particle part. And then in here, it kind of goes down exponentially. And that's, the penetration of the particle into that classically forbidden region. So that's what we were talking about, is that connection. And these critical points are important because they're set the kind of boundary between where the classical motion would stop and then where quantum mechanically you're still allowed to tunnel in there. So they're called turning points because that's classically where the particle would just turn around. But, again, the quantum mechanical description is different. You don't have Newton's equation or something. You have a Schrodinger equation for the wave function, so it's a little different. But of course, it's all the same physics. And so we're just looking at that. We're looking at what happens to the Schrodinger equation in the case where in these regions, you're basically behaving like a classical particle in sort of classically aroused regions. And then elsewhere, we're going to assume that basically what happens here is when you're in this forbidden region, then if you're close to the classical limit, then basically the particle is not going to be found there, right? You'll have very steep sort of exponential decays in those regions, and the wave function will just go to zero very quickly. But we're trying to develop that and understand how that works by actually trying to define precisely what we mean by a classical limit. And we know that it should have something to do with h bar, right? If we send h bar to zero, then that should correspond in some sense to a classical limit. So, but of course, as I like to emphasize in this class, there's no such thing as sending a dimensionful quantity to zero that's not an appropriate expansion parameter. When you do a Taylor series or anything like that, you can't expand in a thing that has dimensions in it. It's just not allowed. Can't do that because it makes no sense, because depending on what system of units you use, you can then make that parameter big or small, however you wish. So it doesn't make any sense to talk about whether or not, h bar is going to zero or not, because h bar has units. So you always have to say h bar going to zero relative to what. But that's the idea, is that that's the classical limit. Okay, so where we were last time, sort of a long intro, but again, I want you to kind of, sort of appreciate the conceptual reasons why we're looking at this, I guess. We're just trying to understand what happens as you make your system more classical. And again, to do that, we do want something like h bar goes to zero. But again, you can't do that unless you have a dimensionless quantity. So we're just non-dimensionalizing our equation. As usual, that's the thing you want to do when you have a complicated Hamiltonian or something. You want to get rid of all the parameters as much as possible until you're left with just some numbers, pure numbers, no dimensions. And the way you do that is you rescale things. So you rescale things that have units. You have a length in your equation, that's the x, so you divide it by some characteristic length scale. I don't know what that is. It could be like the size of your potential well, but, it's something. We're just doing this sort of abstractly for now. And then you have some characteristic energy that's sort of like related to the depth of your potential or something. So you divide by that too. Your energy gets divided by that. And you rescale these things. You do a chain rule on the derivative. And again, you divide by the characteristic energy. And you can rewrite the Schrodinger equation into this form, where now this thing out front here is a number, because this is multiplying just the derivative with respect to z, and z now doesn't have any units. So there's some number, and it's related to the ratio between h bar and this length scale, the characteristic length scale of the problem, and the characteristic energy. And it's multiplying this function, which is the difference between this rescaled energy and the rescaled potential. And we're going to call that q squared. Why? Because we know we want to look at the region that's sort of classically good. And in that region, we know E is bigger than V. That's classically okay because it's positive kinetic energy. So in that case, this q squared, we're going to look at it positive q, it's a positive thing, because this is just the energy minus the potential. And so your equation then reduces to this guy, where, this is dimensionless now. You have quantity q squared divided by this delta squared, with delta we're sending to 0, making it small. Q is this function related to the energy minus the potential. So yeah, and then the idea is that in the WKB, we're going to assume that Q is slowly varying. And the reason that kind of makes sense is because we know that classically the wave function will be very wiggly in this region. So it'll be, you know, varying very rapidly, the wave function, compared to the potential itself. Because at high momentum, you know, you get more wiggles in the wave function. So compared to the potential, though, will remain relatively unwiggly in this approximation, just, you know, at high momentum. And so that's the idea. But before we do all that, I mean, it's going to be a perturbation theory. It's going to be a perturbative approach, but in a kind of transformed variable. So you take your, again, so what's the idea here? If Q is constant, right, then the solution to this is just exponentials, right? They'll look like this, plus or minus IQ Z divided by delta, if this guy is constant. So that inspires us then to look at a variable transformation. What we do is we just say, well, suppose psi of Z is a constant times this exponential of some other function divided by delta. And we know this other function is going to be like something like Q times Z. But in any case, the fact that this is a solution at constant Q, you know, that inspires us to do this variable transformation. So that's what we do. We just substitute this back into this equation, and we get another equation which looks uglier at first glance. It kind of is, but it actually lets us do the perturbation theory. So we plug this back into here. We start taking derivatives, and we get this equation here. So here we plugged in, multiplied through by delta squared. So again, you can rewrite this as delta squared d squared psi. dz squared is equal to, or, you know, plus q squared psi is equal to 0. Then you can substitute this solution into here. You get this delta squared times, you know, two derivatives. You got to make sure to use the chain rule. So if you hit this form with one derivative, you pull down a factor of I over delta times the derivative of this phi function times the exponential again. Then you do the derivative again, and it'll hit both of these terms. It'll hit this derivative term, and it'll hit the exponential again. This just comes along for the ride. So you have when it hits the derivative, you get a second derivative term. When it hits the exponential again, it pulls down another factor of I over delta. So that I over delta cancels this delta squared out here. And then this again just comes along for the ride, same term. Then the exponentials cancel everywhere. And you're just left with this equation here. Let me rewrite it. It's I delta phi, two derivatives with respect to z, minus phi prime squared plus q squared is equal to 0. This is a Schrodinger equation just rewritten in terms of this variable. But it's nicer now because we can now do the perturbation theory in delta. We can start expanding everything in terms of delta. So yeah, any questions about that so far? Just to set up for the general philosophy. We rescaled stuff so that we could send h bar to 0 properly as a dimensionless number. We recognize that if we do that, it's hard to figure out what's going on with just the Schrodinger equation by itself, because if we send delta to 0 here, it means this term gets bigger and bigger compared to this one, but then there's nothing to balance this term. So that's not good. So you have to use an additional assumption. And so you think, well, if delta is going to 0, h bar is small, then you're going to the classical limit where you have large momenta in the classical limit, and the wave function is very wiggly. So maybe we can assume that relative to that, the potential is going to be sort of smoothly varying or slowly varying. So it's approximately constant. And so then we can use a slowly varying assumption to make a variable change from our wave function to an exponentiated thing. And this is the key WKB approximation. It's the first thing you do in any WKB analysis. You say, okay, fine, let psi be equal to a times an exponentiated function. And then you substitute that in, and you might think you get an uglier equation, and you do, but this equation is much more easy to interpret in terms of the delta goes to 0 limit. Now it's real easy. You send delta to 0 and just this term drops out. It's second derivative term, and then you just have a first derivative term, and then you can solve that. Okay, so that's what we're doing. So yeah, so now it's not next time anymore, it's this time. So now we're gonna do a perturbation theory in the function phi. We're gonna assume phi is some Taylor series in delta, and we're going to solve the equation order by order in delta. So the first order, you just send delta to 0, and you get phi prime 0 squared is equal to q squared. Well, if you take the square root, you get plus or minus, right? You get the two roots, and so phi, and then you just integrate. So the solution here is plus or minus the integral. Now you need some kind of bounds for your integral. And we're going to look at a problem like this, where we're going to say, you know, if we go to this rescaled coordinate z, we're going to say that this left turning point starts at some a. So we're going to look at all the z's out here, z bigger than a. So our limits of integration for this problem are going to be from a to out to some z that we're looking at. And this is q with some variable of integration z bar. So that's a solution of that differential equation. Okay, and if q is constant, of course, then we get what we would expect if q is indeed constant, then we get plus or minus q z minus a. So that's what we expected anyway. Okay, so then we go to next order in delta. And now we have to retain that double derivative term, but we don't have to expand phi anymore because it's already proportional to delta. So we got phi 0 double prime. You don't have to include phi 1 or anything because that would be delta squared. Then we have minus. Now we have to expand this guy. So to order delta, only that cross term will matter. So this is, you know, phi 0 plus delta phi 1 prime and so on. So it's only the cross term. When you multiply this guy by this guy, that'll be of order delta. Everything else is either, you know, lower order or higher order, like delta squared. So there's a cross term, which is 2 delta phi 0 prime phi 1 prime. And then you know, that's good. And then the q squared, of course, is not there because the q squared doesn't have any deltas in front of it. So that's it. And then this, now we can use our previous equation to plug in for phi 0. So this becomes I delta q prime. So it's just fundamental theorem of calculus. You take a derivative of phi 0, you just get back out q, because this is the integral of q, so the derivative kills the integral. And if you differentiate again, you just get one derivative of q. And then this term is minus 2 delta Phi 0 prime is just going to be Q. That's that fundamental theorem of calculus. And then it's phi 1 prime. And all of that has to be equal to 0 because there's no Q squared term. So that's a differential equation for phi 1 prime. I can actually write out what it is. D phi 1 dz has to be equal to I divided by 2 Q prime over Q. And of course, the deltas cancel. At each order, the deltas have to cancel, of course. And this is just a logarithmic derivative. It's the derivative with respect to z of the log of q. So that's real easy. We can just integrate both sides. That cancels the derivative. And so phi 1 of z is equal to I over 2 log q plus an integration constant. And we just want to make sure that the whole thing, this phi, vanishes at z equals a, because remember, we're looking at z's inside this classically allowed region, and we just want to make sure that at a, the wave function just goes away, or we want to make sure that that phi vanishes as we approach a here. So that's easy to do. We can just use this integration constant to satisfy that boundary condition. So phi 1 of z with that boundary condition is just I over 2 log of q z divided by q a. So when z is equal to a, you get a log of 1, which is 0. And this is nice. We want phi to vanish because we're going to be, we can use the boundary condition. We can use the boundary condition at a to sort of fix that. So I'll show you in a moment. So okay, so now we've kind of solved everything to second order in delta, or first two orders in delta. And that's in a WKB. That's basically all you ever do, is just those first two orders. You don't go up higher powers in delta, although you could. So what's our solution then? Remember, we're trying to solve for psi of z, which is, again, we wrote it as some e to the I phi, which now we know is going to be e to the phi 0 plus I delta phi 1, right? And then we know what phi 1 is. Phi 1 is here, and phi 0 is here. And again, now this vanishing of phi should make a little more sense. See, if z is equal to a, then you get an integral from a to a, which is 0. So at z equals a, this whole thing, that whole thing is just 1, right? Because both phi 0 and phi 1 vanish by construction. So this a then, we can fix that to be just whatever the value of the wave function is at a, because this part would just be 1. So that fixes that boundary condition at a. So it's not, the wave function doesn't vanish there. It's just we can use the boundary conditions. I misspoke a little bit. So this phi vanishes, and that lets us use the wave function evaluated at a as the boundary condition. So okay, so let me write up this exponential. This exponential is plus or minus I. Oh, so I'm missing an over delta, right? So it's phi, it's the whole thing divided by delta. So it's this guy, right? It's phi over delta. So I'm missing a, there's an overall divided by delta out here. So it's first term is I over delta integral from a to z of q z bar, z bar. And then it's minus, and the i's, there's an I times I, so you get a minus 1/2 there, minus 1/2 log of qz over qa. And of course, you can cancel the exponential and the log to get psi a square root now, because it's half square root of qa divided by qz. Just from the minus sign, minus 1/2 times the log is, 1 over square root of the stuff that's in there. And you get these two kinds of solutions. And these are the WKB solutions. It says that the wave function in that classically allowed region has this form. These are the left moving and right moving particles in that region, right? The plus or minus, right? Those are the waves corresponding to a particle moving left or right. And instead of a usual wave number here, you have this integral over q, which is, but that is basically just going to be the wave number if q is constant. So yeah, these are this is the WKB form, and this is an approximation to the wave function in that region. And you might ask, okay, but so why, what's the deal? Well, the deal is this only solves it in one region. But of course, you have all those other regions to worry about. If you have a problem like this, what about the classically forbidden region? I mean, you have to solve the wave function everywhere. You can't just solve it in here. That doesn't help you at all. Unless, maybe you have some boundary condition that say the wave function has to vanish, or maybe it's periodic or something, then maybe you could try to, you can figure it, but so far this is just like solving it in one region without any boundary conditions, and it's sort of, those are the two solutions. Remember the Schrodinger equation, second order differential equation, you want to get two solutions in each region and then use boundary conditions and stuff to match. So those are the two solutions. So we have that, and we have the plus or minus solutions, but that's not the whole story, because we also want to match whenever we see a boundary. Now remember before, when we had a problem like this, we would match, like we'd use continuity and match the first derivative, things like that. We won't be able to do that here because this form is more complicated. We're going to have to do something a little bit fancier. It's going to have the same spirit as that, but it's going to be a little bit more involved. But we do know what happens in the classically forbidden region, because there all that happens is that q squared becomes negative. When the energy is less than the potential, right? Negative kinetic energy, so q squared becomes negative. And we know what to do then. We just say, let's define q is equal to some I q bar, and then everything goes through the same way, because now we can take q bar to be positive, and the solution just goes through the same way, right? There's no difference. When we do this differential equation, we can have just q be pure imaginary. It doesn't change anything. All it changes is the sign of this. When you do q squared, the q squared will be negative. And instead of oscillating solutions, you get exponentially growing and decaying solutions. And we sort of know that from when we looked at, the Schrodinger equation in the first semester. So there's no difference here. It's just you do this replacement, And then your psi of z, well, it just has two different kinds of solutions in the, so there's the one that we just derived, which is the classically allowed region. And I'm gonna now not use this boundary condition. I'm just gonna call that some arbitrary constant C1. But of course there's the Q of Z part, and we have the plus or minus solutions. There's the minus solution. And I'm not, it's gonna be from some, from some, there's gonna be some boundary over which we evaluate this integral, but I'm not going to say what it is at the moment. It'll depend on the problem, but I'm just going to write out the two solutions. We know that we can combine them linear combinations however we want, because both are valid solutions, the plus and the minus. So we have this, and this is in classically allowed regions. And then we have solutions in the classically forbidden regions that look just very similar to this, except instead of Q, we have Q bar, which is just taking Q and making it in I times Q bar, because we know that in the classically forbidden region, Q is pure imaginary. So we just transform variables. And now, since it's pure imaginary, you have, instead of oscillating solutions, you have the exponentially decaying and growing solution. So one is the exponentially decaying solution. And now the boundary could be something else, B, say, and now it's Q bar. And C4 would be the exponentially growing solution, or the exponential with the opposite sign. And this is in any classically forbidden region. Okay, so now we have we're like solving the Schrodinger equation just like we did last semester, where in each region we have two kinds of solutions, and then we're supposed to do something to match them, right? And in the original, when we originally solved the Schrodinger equation, we simply just matched the derivative and the wave function, right? We made it continuous, and we matched the derivative too. But here we run into a big problem at the turning points where we're supposed to match these things. And can anyone tell me what happens when you are at one of these turning points? Like if you're exactly here, what happens to these solutions? Well, what happens to Q?
The integrals go to 0, right?
Yeah, the integrals go to 0. But even worse than that, Q goes to 0, right? The integrals go to 0, yeah, if these are turning points. Of course, the integrals go to 0, but it's worse than that. remember Q is the difference between the energy and the potential. So epsilon minus the rescaled potential. It's Q is square root of E minus V divided by characteristic energy scale. At the turning points, E is equal to V. That's just by definition that your energy is equal to your potential there. So Q vanishes to 0. So that's not great. That makes it very difficult to match this because all of a sudden all of this stuff becomes singular. The Q's vanish, you get weird singularity. You're gonna have a very hard time matching that. So you have to glue those two regions together by zooming in to the turning point and actually figuring out what happens there. You can't just plug in matching conditions at the turning point. It doesn't work because Q is 0 there. So I don't know what you would do. So you have to glue the two regions together. You have to zoom in real close to the turning point and solve the Schrodinger equation there. And then that lets you glue these two kinds of solutions together. So if you do that, if you zoom in to one of these turning points, let's say occurs at Z naught. If you zoom in there, well, you have your energy. And then we know over here, the potential is kind of below Z naught. And then here, the potential is above Z naught. That's one kind of turning point. You could have the opposite kind of turning point where you go from a classically allowed region to a classically forbidden one. That would be another kind of turning point. But in any case, if I zoom in close enough here, we just pass through Q is equal to 0 as we go through the turning point. So if you zoom in here real close, then that you should have just some kind of linear function, right? It'll certainly come in with some slope because it's passing through E. Or equivalently, Q is passing through 0, going from positive values to negative values, Q squared, or going from negative to positive. So, as it does that, it'll come in with some slope. So around these regions near the turning points, you would have that Q squared is some linear function. So to understand that, it's good to move to new variables. We're going to define a new variable W, which is some constant alpha times Z minus Z naught. And we're going to figure out what alpha is in a moment. So we're going to change variables. And remember our original equation in terms of the Q squared is back up here. It's this guy right here. D psi squared to Z squared is minus Q squared over delta squared. So we're going to go back to that. And we're going to change variables. So d squared psi dz squared. If we change variables to w, that's just going to be alpha squared d squared psi dw squared. And that's has to be equal to minus q squared over delta squared psi. And again, we're going to assume now that q squared is some linear function. And we're going to assume that, q squared is some g, which is the slope times z minus z naught, which in terms of this alpha variable is G, in terms of this W variable is GW over alpha, just by definition of W. So this whole thing we can write as minus GW psi divided by alpha delta squared. And now we can choose our alpha appropriately to get rid of all those pesky constants like G and delta squared. So you define alpha to be equal to G over delta squared raised to the 1/3 power. Because I can rewrite this equation, W squared is equal to minus GW over alpha cubed delta squared psi. So if I choose alpha cubed to just cancel these G's and deltas, then I would make this choice. And then it's really easy. This equation just becomes minus W psi. Now we got rid of everything. And now we're going to make some assumption here about the kind of turning point we're looking at. And the first kind we'll look at is this kind, where you go from positive Q squared to negative Q squared. So from classically allowed to classically, from classically forbidden to classically allowed. So it would be like the left turning point here in this picture up here. You go from classically forbidden to classically allowed. So, oh, sorry, is that right? Q squared. No, sorry, it's this other one, right? Yeah, Q squared is positive here because E is bigger than V. Yeah, it's this kind of turning point too. V is bigger, so Q squared is negative here. So it passes through. So Q squared goes from positive to negative. So that's the kind we're going to look at. So it's sort of the opposite. We're going to look at the opposite one, this one. So here in this region, the potential is lower than the kinetic energy. The potential is lower than the total energy, so Q squared is positive. And here to the right of it, Q squared is negative. So you go from positive to negative, so that's a negative slope. So we're going to really look at minus G, right? And for Z is smaller than Z naught, then this is positive, and for Z is bigger than Z naught, then this is negative. So you go from positive Q squared to negative Q squared as you pass through Z naught. So it's this kind of turning point from classically allowed to classically forbidden. So that's, and so you can define G with whatever sign we want, but it's convenient to just look at that first. So this G we'll assume is negative, or we'll define it to be positive, but we'll just put a minus sign in front of everything. So this just becomes a plus. This minus sign will kill this minus sign. So overall, we just have a plus sign. So this is the differential equation we want to solve. It's just two derivatives of psi with respect to W is equal to W times psi again. Well, you can look up what these solutions are. You know, it's second order differential equation. There's two solutions as usual, and this is the Airy. These are the Airy functions. This is the Airy differential equation, and there's two solutions, and they're given by the two kinds of Airy functions. There's the A ones and the B ones. And you can sort of look up what they are. They look like kind of decaying, oscillating things. But the point is that they have asymptotic behaviors. We can look at them for large W, for large positive and negative W. But these are the two solutions. Linear combinations of these form solutions to this second order differential equation. But the point is that they have asymptotic properties, which you can look up or you can derive actually. And I might do that in a recitation if there's some interest, but you can look up what happens to them for, say, W is, large and positive and W negative. They'll have different behaviors those two kinds of solutions have different behaviors for positive and negative W. For positive large W, they look like 1 over 2 square root of pi W to the 1/2 power. So it's like W to the 1/4 e to the minus 2/3 W 3/2. That's what the A's look like. And we sort of know that this is sort of kind of what it has to be, because remember what the situation is. We're going from classically allowed to classically forbidden. So we know that in the forbidden region, right, we would expect to get kind of exponentially decaying solutions there. And that's the same for a linear potential, right? We're just solving basically a linear potential problem with the energy kind of, going through the center there. So if W is positive, then we're in that forbidden region. So we should get exponentially decaying solutions. And that's what happens with the Airy functions. They exponentially decay, these guys. And of course, the B ones are the other solution, which are the exponentially growing ones. So the B's are the exponentially growing versions of that. And they have slightly different normalizations. But that's okay, again, because it's linear combinations of these that form solutions. So it's that's fine. There's these funny powers, but still it's just exponentially growing and decaying solutions. And that's what happens for large positive W. And for negative W, we should get oscillating functions, right? Because that's the classically allowed region. Remember, these solutions are nothing but solving for your wave function in this case, right? Where your energy is here, and it crosses through at W is equal to 0 here, and this is your potential, and we're sort of, this is your potential and this is your energy. So over here, we get, if we plot the wave function, we should get exponentially decaying stuff out here. And then over here, it should start, oscillating. And it gets more and more kinetic energy as it goes out here, because this potential keeps going more and more negative. It's just a line. So this thing should kind of keep oscillating. I think there was something like this on one of your tests. You were plotting, I think it was on the final, you were plotting a wave function for like a linear potential like this. These are the Airy functions. You were like intuiting the shape of the Airy function. So this is AI. The B ones, of course, is the exponentially growing version of this, but it's a similar idea. Okay, so the oscillating parts look like AIW is 1 over square root of pi W 1/2, and its cosine here of 2/3 W 3/2 minus pi over 4. It's an important phase shift. And BI in that region is minus it's the sign. And you have to look these up, or you can derive them. And again, I'll do that. It involves some complex analysis to do that. So I don't, but And so now these are the solutions when the potential is approximately linear. So now we can use these solutions to match up approximately linear and far away from this turning point. This is what they look like. You get exponential decay here and oscillations out here. And we can match these guys, these regions, to our solutions here, right? Because this is what we know things look like in the classically allowed and classically forbidden region. And now we know how to glue those two things together. We use a linear ramp kind of, we use a linear potential solution to do that. And there's really no surprise that we get these W to the 3/2 things, because if we think about what the integral of Q is, if we integrate, say, from 0 up to the turning point Z at some Z naught, if we look at, so say, Q over delta, if we were to integrate that, what is that? That's just Z to Z naught of the square root of G over delta squared of Z naught minus Z bar. That's just what the potential is, that linear potential, dZ bar. And we can actually do this integral. That's just 2/3 square root of G over delta squared Z naught minus Z raised to the 3/2 power. And that's nothing but 2/3 W 3/2. So this integral of Z to Z naught of Q over delta, that is 2/3 W 3/2. That is these exponents. And that's exactly, that's exactly what these guys are. So this form matches what we get from a linear ramp potential, as it should, because we know that, far away from where Q goes through 0, we should just be getting these solutions out again for the classically allowed and classically forbidden cases. Yeah, so everything kind of matches up, right? And so we can rewrite these solutions as follows. We can actually rewrite them in terms of the integrals over Q. This becomes C1, some constant C1 over 2 square root of Q bar P, and this is minus the integral from Z naught to Z of Q bar Z bar over delta. And the other kind of solution is C2 square root of Q bar exponential Z naught to Z of Q bar so that's what those solutions are. We can just rewrite them, because the form of these solutions, again, far away, it has to be the same as these solutions that we found. But now the key is that because these solutions are the same function as we move across this linear region, that means if this is the form of the function in this classically forbidden region out here for positive W, then for negative W, we have to have the same function. So whatever the relationship is between the AI here, this guy, and this guy, has to remain. So what is, if we observe here, what's the difference? Well, we see that instead of 1/2 here, we have no factor of a half. We just get 1 over square root of pi W 1/2 across that region. So here in that for negative W region, we would have to have a factor of 2 difference. So this just has to be C1 over square root of Q now because we're in the classically allowed region. And instead of this exponential, we get a cosine. But otherwise, the argument of the cosine is sort of the same. We get the 2/3 W 3/2, which in this case is just integral from, well, now it's a little bit different. It's the integral from z to z naught, because we're on the other side of the turning point, of now QZ bar over delta. And there's this phase shift of minus pi over 4. And similarly here, if this is the form of the, if this is how we write the Airy function in the classically forbidden region and the classically allowed region, just by looking at this guy, what the relationship has to be, there has to be a minus sign. Otherwise, this stuff stays the same. But now it's QZ. And we get a sign now of z to z naught q over delta dz bar, that integral. And there's a phase shift again of minus pi over 4. So let me just, we'll have to wrap up next time, but you see now we have a relationship between the 2 different kinds of solutions. And you see now we know what the relationship is between, say, the C1 coefficient is and the C3 and C4 coefficients is. They have to be related to each other in this way. So if you have a linear combination of these Airy functions, then in the other region across the turning point, then it has to have the C1s and C2s have to recombine to form C3s and C4s such that this relationship holds. And I'll write it out more explicitly later, the exact matching conditions. But the idea is that, you don't just have 4 arbitrary coefficients here. If you start with 2 coefficients in one region, then in this other region, it's not just these 2 solutions, it's particular combinations of them that are related to C1 and C2. And those combinations are just these guys. So you don't get just arbitrary solutions on the other side. You get this relationship. If you have any linear combination here of these guys on one end, then on the other end, you'll get a linear combination of sines and cosines. And that's, I'll show you that more next time, but you should at least get the idea here. Instead of matching remember how we used to do this, right? We would just match the derivative and the continuity. We have 2 equations here, right? And then if we had 4 coefficients, that would reduce those 4 coefficients to just 2. And we did that by the matching across the boundary. Here we're doing the same thing, except we're doing the matching by just solving at the turning point. We're just solving through this region where we approximate the q squared function as a linear function. And so that we just solve that equation, and gives us a way of matching. And so we reduce our 4 coefficients, C1, C2, C3, C4, to just 2 coefficients. And the relationship is just given by the behavior of these Airy functions as we go from one region to the next. The Airy functions include continuity, basically, and that derivative matching is the idea. So we do the matching by exploiting properties of these Airy functions instead. So that's the idea, but I'll finish it up next time and give you an example of how to use it, stuff like that. Okay, any questions?
So I get like the solution and like doing the straight line approximation and all that, but like I don't see how it's really fixing or dividing by 0 at z equals a. It seems like we still have that problem, don't we?
Oh, yes, that's true. But what fixes it is, remember that these forms of the Airy functions, they're only valid away from 0 where things are bad. But the Airy functions themselves, if I were to actually plot them, like in Mathematica or something, they behave okay at exactly that turning point. So we did fix it by just saying that at that point, the shape of the wave function is just going to look like the Airy function. And, you know, and we're okay there because we actually solved that linear potential exactly, right? We solved it without, we went back to the equation where things are okay if we let this W pass through 0. We just solved it exactly in that region. So it's just the Airy function. So that's how it's fixed. It's not obvious how it's fixed here because what I've written is not the actual Airy functions, but what happens to the Airy functions far away from that bad point. And far away from that bad point, those Airy functions should look just like the WKB solutions.